So next, let's welcome David, and again, appreciate David came to Taiwan. He asked me about the topics wanted to share, and then he said I shared that he shared with me several of them, and this is a new one that is going to present in the end of the year. So this is a preview of this talk, and thank you so much, David. We're going to hear something different from you. Let's welcome David.
Thank you very much, Ethan. Yeah, I'm actually kind of nervous about giving this talk. This is the world premiere of this talk, and it's been something I've wanted an excuse to talk about for quite a while, so thank you for giving me this excuse. And I haven't really thought it through. I'm not really an expert in this area, but I just think it's important, so I want to talk about it. So as Yiting mentioned yesterday, I was one of the program chairs for CVPR this year. There's 5 program chairs, and then there's like this big pyramid of area chairs and reviewers and authors for this huge conference with something like 40,000 authors who submitted to this paper, to this conference. And so like I had this very strange experience of on the first day giving the talk about giving the intro to the conference to 12,000 people, which I had never done before. And as I was doing that, I was thinking that this is actually my 25th anniversary of going to CVPR, because the first year that I went was 1999. That's me at the conference banquet, which was held on a buffalo ranch in Wyoming. We all got on buses from Fort Collins, which is where the conference was. We got on school buses and went up to the buffalo ranch for the dinner. It was like a 40-minute drive or something like that. You can just imagine like how you would possibly do that today with 12,000 people, putting them on whatever you need, 500 buses or something to take them to a ranch. And so I was thinking about all the things that have changed over the last, say, 25 years or even more recently in this community. I mean, one is that it has grown enormously. So if you look at the number of area chairs, there were like 20 in 1999. We had almost 600 in 2024. There was something like 100 reviewers in 1999. We had 10,000 reviewers in 2024. The number of papers that have been submitted to CVPR has, of course, been growing exponentially, something like 4 times the number of papers since 2017. This year we had something like 12,000 paper submissions, and of course only a small fraction of those are accepted at all, and only a tiny fraction are accepted as talks. And so there's just tremendous amount of like competition for getting the ideas out there. And other things that have changed is that like now computer vision is in the popular consciousness. So if I just look at like articles mentioning computer vision in like the last month in the New York Times, there's like whatever, 12 of them. Whereas in 1999 I had to go through this big routine about explaining what is computer vision, you know what a computer is, blah, 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 blah. Now we no longer have to do that. And in fact, this field has become so prominent that if you look at the publication statistics according to Google Scholar, CVPR is the #2 most impactful venue in all of science. Like Nature is #1, and the CVPR conference is #2. It's kind of crazy. And so as these things have changed, I think it's natural to ask, like, how has the community changed, and how has it affected the way that we do science? And so a couple of years ago, around 2020, during the pandemic, I was telling my friend Norman Su, who's an ethnographer, about all these exciting changes that were happening in the community and how they seem to be kind of mixed. Like people were very excited about some parts and maybe not so excited about others. And he said, you know, we should actually like study that, because in ethnography that's what we do. We go into communities and we study how the community is and what it's like to be in that community. And so as sort of a passion project during the pandemic, we conducted this qualitative study of what people in computer vision, what researchers in computer vision were feeling about the changes that were going on in the community. So we advertised the study to a really wide range of people. In the end, we got about almost 60 people who responded to this prompt, where we asked them to write a nonfiction story about computer vision with yourself as the main character. And the story should involve recent changes in the discipline and detect an event of emotional impact. And then we went through the stories with them, we helped them revise them, and tried to understand sort of what kind of emotions were coming out in the work that they do. And the respondents, the demographics were not a representative sample of the overall community. Most respondents were in the US. Everybody responded, did so in English, so we're sort of biased in that way. But nevertheless, this study, I think, kind of revealed interesting things that we are all dealing with in this new world of computer vision and all the excitement in it. And some of these emotions that we found are very kind of positive. People talked about the fact that deep learning had rejuvenated a tough and hopeless time before 2012 when there was only incremental progress. Excitement that deep learning is now like this tool that you can use to solve many different problems, as opposed to in the past where you sort of had to hack together a new approach to solve any particular problem. And there was a lot of excitement about like the pride that now computer vision is well known. That there was like this surprising switch in power dynamic, whereas like when I graduated from a PhD, you had to like fight in order to get an internship, whereas these days you have to like fight off the companies trying to give you an internship. In some cases that's true. The conferences are so well funded and all of these kind of events for recruiting students and so on. And people talked about like the moment that they realized how big deep learning was. So there was these stories of like people who you know, we're experimenting with deep learning in 2012, and one student said 30 minutes later we had results that outperformed the prior model by 10 or 20%. I remember bouncing back into my advisor's office with a silly grin. It was an eye-opening moment. And yet this study also revealed a lot of maybe less positive emotions. So there were things like frustration over the loss of what people said were like fundamental questions in computer vision. So they said, well, I got into this field because I was interested in like how people see the world, or I was interested in cognition and vision and learning, and now I feel like I'm mostly a network meta parameter adjuster or something like that. People talked about the hyper-focus on benchmarks and engineering the black box. They talked about things like selective amnesia, that papers that were written just 5 years ago are now forgotten and no longer read because the field is moving so quickly. People talked about feeling isolated, and I was actually very surprised that people, even in like the top universities and the top institutions working in computer vision, expressed this feeling that there's just so many papers, so many people in the area, that it's actually really hard to make your impact on this area. And people talked about marginalizing ethics, the fact that like ethics were not, at least in 2020, and things still to a large extent are not, sort of foregrounded in the conversations that we have at the conferences. Other kinds of negative feelings were things worrying about potential harm. So one person talked about how they used to be a simple, happy nerd, an ostrich researcher hiding their head in the sand, but they can no longer do that, blaming others for the misuse of technology because the technology they're developing could be used for negative purposes. They talked about the uncertainty of where the whole field is going. Some people talked about specific papers that they felt were harmful to specific people, especially in the way they treated things like gender, transgender people, things like that. And then there was sort of mixed feelings about all of the hype that's coming from industry around deep learning. They're saying about how it's hard for academia to compete, for example, in a world where Facebook and Google and so on have so many GPUs and so much data. And so the takeaways of this paper, this paper was actually published in CVPR. One of the most daring things I think I've ever done with my tenure was to submit this paper to CVPR, and I thought it would just get totally trashed because it has absolutely no equations, there's no results tables or anything. But actually it got a strong accept, and people seem to actually like it. So if you're curious, it's a pretty easy read, and I'd suggest that maybe you read it. But sort of the takeaways were that the computer vision, the growth of computer vision is having all these kind of mixed impacts on people. And like as researchers, we don't, and especially in computer science, I don't think we really think of ourselves and the emotional impact that our work has on ourselves. And I think it's sort of important to keep that in mind and remember that we're sort of all going through these kinds of things together. So that is one thing that we were thinking about. And then we started thinking about, so this is like the effect of people, the effect of people on the community. But we were also interested in how has all of these changes affected the way that we publish papers and the kinds of papers that we publish. And so my student, Sam Gorey, who's now an assistant professor at Stonehill College, he graduated last year, has this paper that'll appear in CSCW this year. It's called "Attention is All They Need, Explaining the Media Archaeology of the Computer Vision Research Paper." So what he did is he looked at like 20 years of computer vision research papers and used a mixture of both quantitative analysis of what was in the papers, including the visual layout of those papers, so also some hand coding. He also interviewed a bunch of senior computer vision researchers so that they could sort of reflect on the papers that they had written and how they had changed over time. So I'll just sort of give some high-level ideas from this paper. One is that, so some of the changes in the way people publish is due to technology. Of course, there's the technology of computer vision that has changed, but there's also the technology of how we publish papers. You know, in 1999, CVPR papers looked like this. It was hard to publish in color because they were reproduced in black and white. You had to like pay extra if you wanted a color page at the end of your paper, and so on. Nobody read it in PDF form. They got a physical copy of the proceedings, which they took home with them, printed out to read the papers. Whereas, of course, now these days there's no such thing as the paper proceedings, and that means that you can load so much more content into your paper because you can make really tiny images that people can zoom in to see them, for example. So just the amount of information that's packed into the same 8-page paper is tremendously larger than it was before. And then there's also other sort of striking statistics, the striking kind of pattern. One is that there's been this sort of rise of acronyms in our community. So if you look specifically, for example, at acronyms in the titles of papers, you'll find that these days this is very common, right? GF Pose, CX Tract, Noisy Twins, etc. Like each proposing a system name for their paper. This is a fairly recent phenomenon. People didn't used to do this, and now in 2020 it was like 40% of papers. At CVPR 2024 it was over half of papers did this. Another kind of interesting trend is the rise of teaser images. So teaser images are these big like hero images that you put right at the top of your paper to kind of lure people's attention right away on the first page. This also used to be very uncommon, even 10 years ago, and now I think in CVPR 2024 is about 20% of papers with this. There's also been the amazing rise of the results table. So in almost every computer vision paper these days, there is table 1. Table 1 is extremely important. It has all of the comparison of your results of your algorithm to all of the recent algorithms on some public benchmark data set. Your algorithm is almost always listed last. Your algorithm almost always has all of the entries in bold, which shows that you have the highest number in the table. And this is extremely important in the sort of way that we write papers these days. This is also relatively new. Like in 2013, only like 3/4 of papers had a table at all. And now basically they all do. And so if you think about like what today's computer vision research papers look like, they have this idea of branding a new model with a catchy name. They have this teaser image where you sort of compare yourself to the competition. They have the quantitative comparisons to competitors showing improvement. And it reminds me maybe of something like in ad on television, where you're like trying to sell your paper towels. And you're saying, now Bounty brand paper towels, they work, whatever, 2 times better than the leading brand, and here's an image that shows how much better they are. It seems like so much of what we do now in our papers is marketing. We're trying to actually engineer the paper to get accepted into the conference. And as the program chair for CVPR, we saw all kinds of evidence of this, where people are motivated primarily by trying to get their paper in, as opposed to doing interesting work that the conference would want to accept. And so, there's all kinds of things, people plagiarizing other people's papers, people hacking into open review and trying to withdraw the competition's papers, like all kinds of crazy things that you can imagine. that seem driven by this idea that the goal is to get your paper into CVPR. It doesn't actually matter what it says. And so I was thinking about, like, what is causing this and what we could do about it. We can't wave a magic wand and make it so that, like, people no longer count citation metrics in our community. We can't make H indices go away. Like, people are still going to try to get their papers into CVPR, and because that's important for getting tenure and getting a job and getting a PhD or getting a master's degree or whatever it is. It seems kind of bad that we have these quantitative metrics that encourage people to, like, count citations and get their papers in the cost, but we're probably not going to fix that. But I was trying to think about, like, in the process of doing research, the papers that we do, the work that we do, like, how can we sort of step away from this and make sure that we are grounded in something a little bit more than just trying to get better numbers than somebody else? And so my student Sam, who has done a lot of reading in, like, philosophy, for example, and other areas, had pointed out some work that I thought was super interesting. So there's this paper by Donna Haraway called Situated Knowledges. And she suggests that all views of the world come from somewhere. We see bacteria or stars only with microscopes or telescopes that we build. In other words, as scientists, we think of what we do as being purely objective, like we're trying to measure the world and we're trying to report our findings. And we pretend like that's completely objective, but it really isn't, because every step of the way we have to make subjective decisions. We decide which research questions to pursue and which ones not to pursue. We build the instruments and the methods in order to try to answer those questions, and there is involved in them many different choices. And our background, our unconscious biases and so on direct some of those choices. And so treating things that are objective that are not objective can lead us astray, can reinforce majority viewpoints at the expense of others. There's a lot of examples in the history of science of people who used scientific facts in ways that they shouldn't have. So for example, like somebody mentioned IQ scores, for example, there's a very long history of people using IQ scores to argue, for example, that some races of people are more intelligent than other races. There's this horrible history of that in the United States. When, of course, the intelligence tests were designed by, like, white men and made assumptions about the cultural background that you had, and if you didn't have the same cultural background, you were almost destined to fail. There's all kinds of other examples like this. Haraway calls these things God tricks. These are the things that we pretend are objective but are not really objective. And so I was thinking, like, what are the God tricks that we do in computer vision without really even thinking about it? What are the assumptions that we make in these papers that we write? And so I think there's some that are very obvious, and probably if we all stop to think about it, we come up with a similar list. There's things like we treat image data sets that people have collected and that we help download from the web or whatever, as if they are, like, representative of the visual world. When, of course, like Microsoft Cocoa, for example, and ImageNet, they're based on images that were uploaded to the web, which means they are biased in the sense that some photographer decided to take these images, upload them to the web. Some researchers had to decide which images to select to put in the data set and which ones not to select. They had to decide which objects to label and which objects not to label. Each of these involved all of these subjective decisions. But then at some point, all those levels of abstraction fall away, and we get to the point where we're writing our CVPR paper and we're saying, look, on ImageNet, I get whatever 99.2%, Yiting gets 99.19%, I am clearly better. And it also leads us into things like the fact that the paper by Timnit Gebru and others who showed that, like, face recognition algorithms a few years ago worked much better for middle-aged white men than they worked for other people, among other reasons because a lot of the data sets that people had used historically for training and testing computer vision face recognition algorithms were either collected mostly by white men taking pictures of each other, or later there were things like Celeb1M dataset, which were an attempt to get more diverse faces, except they were downloaded from celebrities' images on the internet, and the people who become celebrities and are frequently photographed on the internet are not a representative sample of the whole world's population. So that's one God trick. I was thinking of other God tricks are things like we think of photographs as if they were objective measurements of the visual world. And yet, of course, they're not. As you know, when you take a picture, there's all kinds of things that are happening. There's the fact that the 3D world is being projected into a 2D plane. There's the fact that we have to represent the colors in a particular way. By the way, probably in Yiting's image processing class or something, you learned about color models. Kind of interesting that the whole color system, that all modern like display technology, projectors, photography, television, everything depends. Those color models were actually created by only by observing 17 observers back in like 1931 or something like that. And that became the standard observer by which we model all of humanity based on these 17, I think, British people back in the 1920s. And so like things like that, there are these assumptions that were made, and then those assumptions control the observations that we get when we take a picture. So these photographs are not objective measures of the real world. And then of course in any modern digital camera, there's all these kinds of post-processing that occur. So even if they were an objective measure of the world when you took the picture, they're no longer by the point when that image processing chain is over. Or another God trick I'd argue that we do is that we treat evaluation metrics as if they were perfect, objective, and unbiased measures. So this is just a random table I found in some paper. I didn't even cite it because it doesn't really matter, and I didn't want to pick on anyone in particular because we could make this case of any paper. This paper has all of these numbers. The numbers are according to certain metrics, and then we, of course, use these metrics to compare different algorithms, and yet in each of those metrics, behind each of those numbers, were a huge number of decisions. There were ground truth labels that had to be collected that these numbers are based on. There's the fact that we decided to use average precision at various thresholds of recall. There's all sorts of thresholds and decisions that are made along the way in arriving at that single number. And so we have to remember that that single number is just one view of the way that our algorithms are working. And then I was thinking that more fundamentally, and this actually relates to some of the discussion that was happening before with the questions to Yuki, is that we treat vision, as computer scientists, as computer vision researchers, we treat vision as sort of this unambiguous, objective process. So I think intuitively, I see the world in a particular way, and I assume that everybody else sees it in the same way. And yet that is not true. First of all, vision itself is ambiguous because we see a 2D projection of the world, and from that we have to infer the 3D structure of the world. And of course there's lots of different 3D worlds that could have created this 2D image. This is the particular one that was created here where the 3D effect only looks right from one particular angle. This is Julian Bieber, who's a super cool chalk artist who makes these drawings like this. But more fundamentally, we do these kinds of assumptions all of the time in trying to understand the visual world. So for example, here's a little video that I like. We're making all kinds of inferences as we watch this. And many of the inferences you made were probably wrong, because vision is this inherently ambiguous process. And then we treat vision as if we're measuring the physical world, and yet we are not, as I'm sure you've learned in these things classes, like color, for example, is this sensation that people have. It's not a physical property of the world. You can't measure color. You can measure distribution of light over different frequency spectra, but you can't measure red or green or blue, right? And so there's all kinds of examples of this. You've probably seen examples like this, where if I ask you, like, what color is this and what color is that, most people will say this is blue and this is yellow, and yet it turns out that they're exactly the same color. Or another example, you've probably seen this one, maybe I ask, what color is this? What color is that? Let's say that's brown, that's yellow, but of course, they're exactly the same color. And so then the question is, like, is this an illusion? Or, like, what is even the right answer? Because vision is something that we define in terms of humans' perception. Again, it's this sensation. So is this the right answer? Is it the right answer that these two squares are the same color? Or is it the right answer that this square is yellow and this color is brown? I think this is, right, reveals the fact that what we are trying to solve here is not objective. Vision is not some objective thing that we're trying to do. Another example that I'm sure you've seen before, so in this case, most people see these illusions the same way, but then there's other kinds of stimuli where we all see them in different ways. I'm sure you have seen this, the famous picture of the dress. And so some people tend to see the dress as a white dress with gold stripes, and other people tend to see it as black dress with blue stripes. Just out of curiosity, if you had to choose one of those, white dress with gold stripes or black dress with blue stripes, how many people would say black dress with blue stripes? And how many people say white dress with yellow stripes? So there's 4 of us. Okay, so we're in the minority, but I am telling you that must be a white dress with yellow stripes. I can't see any other possible way. And what's very interesting about this image, so there's been plenty of papers and even like special issues of journals trying to understand why this happens. And you know, one explanation is it sort of assumes what kind of illumination you are assuming that's going on here. So this is actually what the dress does look like. So the black on blue people are correct. But what's kind of interesting about this, not illusion, but stimulus, is that it tends to be persistent across long periods of time. So in other kinds of illusions, you might see one thing and the other thing back and forth, depending on where you look. This seems to be very stable. Every single time I've seen this, it always looks white with gold stripes, and I can't, no matter how often I look at it, can't make it look black with blue. So, like, what's the right answer for a computer vision algorithm? I don't know. And then everybody's hardware is also different. So even, this is like some cognitive thing probably that's going on, a higher level visual processing thing, but it's sort of the hardware level. We also have the fact that each of our color vision is slightly different, some dramatically different than others. So for example, I see 16, and then I see nothing and nothing, and then I see the word no. And I don't even remember what is the right answer here. Do you see it? 6, and that's 2. And do you see no? Exactly. So, hence my point. That's because I'm red-green colorblind. If you see what I see, which is 16, nothing, nothing, no, that might mean you're red-green colorblind too. But each of us then sees the world in a completely different way. So we have to, I think, as we build computer vision algorithms, remember that what we are doing is not trying to solve some objective truth about the world. There has to be, like, you have to be thinking about people, because it doesn't even make sense to be thinking about vision unless they're somehow connected to a person, like a visual observer. And each of us sees the world in different ways. So as an example of this, we have this paper at AAAI last year, where my student Sam and postdoc Wesley got interested in a sort of a particularly extreme case of a situation where people see different things. And that's in aesthetic quality assessment. So there's a variety of papers in computer vision and multimedia literature where the goal is to build a system that will take an image and tell you kind of how good that image is, assign an aesthetic score, quality, how nice of an image it is. And so there's various data sets where they collected a whole bunch of images. Of course, they played some God tricks by deciding which images to put in there. But then they present each image to usually a couple of observers, maybe 2 or 3 observers. They ask them to rate how good an image this is. They take that as an average, and then that's the ground truth, and then they try to develop computer vision algorithms that can match that prediction, predict that same ground truth label. So we can ask, I think, some questions here. One of them is maybe, does it even make sense to assign a quantitative score to something like the aesthetic quality of an image? And so to answer that, my student Sam did this exercise where he took one of the existing data sets, which is called AABB, and he relabeled it with many more people. So instead of having just 2 or 3 people label each image, he had in some cases like almost 200 people label the images. And also, instead of asking people to just rate an image like on a scale of 1 to 5 how good an image that is, because that's a very ambiguous question, he instead asked people to do this sort of forced choice kind of methodology where you give 2 images and you ask which one do you like better, the left one or the right one, or about the same. From those forced choice decisions, then you can infer labels on single images using methodology that's very standard in fields like psychology and vision. And so then, using this new data set, he could then look at the original ground truth labels that came with the data set and see how well those ground truth labels predicted the labels of these new observers. Yeah, sure. Right. Right. Mostly, in this case, he wanted dense labeling of certain images, so I think every participant saw some of the same pair of images that he had chosen ahead of time. There's something like 20 images. I think there are like 20 images that he wanted all participants to look at for various reasons, and so those were not random, but then the others were basically. We did ask people to do that. We didn't ask people to do it for all of them because it was too hard, but we asked them to do it for some subset. Yeah, exactly. Yeah. I'm not going to show any of those results today, although they're in the paper. The answer for those, the keywords, is that like people made decisions based on all kinds of different things. The content, whatever. This image has a gun. I really love guns, or vice versa. That kind of thing. So we did this. We did this relabeling, and so then we had kind of 2 sets of average aesthetic scores. One were the ground truth presented in the AABB score, which is supposed to be like humanity's objective judgment of how good this image is. The other is the average score from our participants. So we could take an average of all of our participants and say that would be our ground truth if we were to collect this data set the same way. But using those 2 like ground truth data sets, we could then see how well those ground truth actually predict the individual aesthetic judgments that individual people gave. And it turned out it was very poor. Like across the 200 people, there were just huge variations in the scores that they gave. And so then we thought, well, a common thing to do would be to say, okay, and there's papers in the aesthetic quality literature where you're like, well, it must be that the reason for these variations is that certain kinds of people like different kinds of images. And so we looked at like all this demographic information to see like whether there were certain correlations that would predict in demographic data what kinds of images people would like. There were no correlation. There were some things about image attributes that were correlated, some things about the image content, like rifles were very negatively associated, other things like dragonflies were apparently positively associated, but there was not really any signal in any of this. And then there's a bunch of work in this area that looks at personalization, so where you take some aesthetic judgments from a particular person, and then sort of fine tune using that small set of judgments that were given by a particular person, and try to then infer what other photos that single person would like. So using this data set, we were actually able to do this at a larger scale than before. And we found basically that the prediction accuracy after you go through this personalization process increases very slightly from 42.6% to 42.7%. But really, there might just be a fundamental problem with this kind of image aesthetic quality assessment problem, where just people are so diverse in the images that they like, and it's really difficult to like boil everyone down to a single average, or even like a few groups of average, a few groups. And so like our takeaway of this was this predictive ability of the ground truth that people use in these aesthetic quality assessment databases really varies greatly from person to person. And it's just, maybe it's not, you can't just sort of get rid of the subjectivity by fine tuning or something like that. There's really this kind of fundamental problem. And if we fail in this idea that we can somehow objectively model something that is clearly subjective, then we create systems that, for example, might discriminate against some people because they represent some users' taste better than others. Now, it's not necessarily clear like what the solution is. Like I just did this takedown of this area, but I didn't offer a solution. My student Sam had one potential solution. It's not really a full-blown solution, but it might be a step in the right direction. It's at least an alternative way of thinking about evaluation. So he was thinking that, you know, yesterday I talked about egocentric or wearable cameras, and he was thinking about the fact that third-person photographs like this one tend to be sort of very clean and somewhat artificial because a human has chosen it based on some reason, and then they've chosen to maybe upload it to the web, for example, whereas egocentric photos are maybe messier because they show what's in front of the camera regardless of the quality of that image. And so like going back to this Donna Haraway's God tricks, we talked about how there's various kinds of God tricks. One of them is, if I organize them in two very broad groups, one is like treating photographs and photo data sets as objective views of reality, and the other is treating benchmark evaluations as objective views of our models. So in some sense, if we use egocentric cameras instead of like third-person cameras, you might get away from the first of these, because you can say, well, now if we're just collecting egocentric cameras, we're looking at sort of the images of the visual scenes people actually see. We're not like hand choosing the objective. We're not hand choosing the third person views. But the second part we still haven't solved. This idea that there's benchmark evaluations and metrics that we use as objective views of reality. In other words, what we do in computer vision usually is somebody collects some data, then we like have a bunch of people, well, so we have a bunch of people collect data for us, typically by just downloading their images from the web or something. Then we might have a bunch of Mechanical Turk users label those images. Then we forget about those people. And we go off into our job of like building machine learning models and testing on training, splitting the data and training test splits and all that kind of stuff. And then we get benchmark evaluations and we publish our paper. So Sam's idea was, what if instead we involved the original people who collected the data in the evaluation of the algorithm itself? So then, like, the people collect data for you maybe, you go off, build some models, whatever, you do some your own evaluation, but at the end, you go back to the people who collected the data and you ask them to evaluate the system that you created. So now you can no longer just create your own arbitrary benchmark data set to get the best results, because those people are in the loop deciding whether or not your algorithm is good. And so he built this kind of, for his PhD thesis, he built this kind of alternative evaluation way of doing evaluation. It's very speculative, it's very hand-wavy, but the idea is you can create like an app. The app has no shutter button. You don't decide when you take a picture. Instead, it's always taking images as you use this app. And the app in real time is running different quality assessment algorithms, and it's telling you what its output is. And so this is sort of a natural way of a user being able to use the image, use the algorithm that you built, explore their own environment with it, see which kinds of things the algorithm is responding to and which things it isn't, and do like a qualitative evaluation of this algorithm. Now, you can't really do this at large scale, and there's still the need for quantitative evaluations and so on, but at least this is maybe an alternative way of getting around some of these problems with God traits. So, by the way, if you have to go to class, feel free to, you won't bother me. I can, as faculty, we are extremely good at giving talks, even if nobody is listening. So I would give this talk even if you weren't here. Okay. And so that's one example of maybe taking a more human-centered way of doing the evaluation, where instead of relying on some quantitative metrics that you chose, you instead involve human subjects in the evaluation process. And then finally, I'll just talk about one other project that I think kind of took more this human-centric kind of viewpoint. And it's actually a very exciting project. One of my favorite projects I think I've ever worked on. It's called Iris. It's this little robot we built called the Interactive Robot for Ikigai Support. So in Japan, there's this concept of Ikigai, which is roughly like your sense of meaning and purpose in life. And this project was funded by Toyota, and Toyota was very concerned about the aging population and helping older adults, especially older adults living with memory loss and living with dementia, being able to live alone longer with more independence and having support in various ways. And so the idea was to create this social robot, which is this cute little humanoid robot that just stands on a desk. You can't walk around or anything, but it can engage older adults in conversation and try to get them to talk about and think about the things that they find meaningful in life, maybe remind them of things that they have forgotten. And so here I can show you a little example. So the goal is to engage the older adults in conversation, get them talking, maybe feel a little bit less lonely, help them reflect on the things that bring them meaning and purpose in life. And there was a cross-cultural component to this also, because we were developing both in the US and in Japan. So we wanted to study various aspects of how to build this system that would work in both places. And so, of course, I can tell you about all of the technical challenges involved in this project. And if I were a computer scientist, which I am, that would be where I would start. Like, I'd be, okay, there's this whole list of computer technical challenges we have to solve. We have to do voice recognition. We have to do voice synthesis. We have to figure out what kind of questions to ask people. We have to connect this with computer vision. We have to develop algorithms to figure out like what people's facial expressions are, what emotions they're happening, when it's my turn to talk, all this kind of like technical challenges that we do. But what I think was so interesting about the approach that we took here instead, and this is due to my collaborator Selma Sabanovic, who's really the brains behind this whole operation, is she developed this whole community of people in local dementia care communities, local nursing homes, other older adults, that became like this community over 3 years that helped us design this robot. And so every 2 weeks, she would bring in a panel into our lab of about a dozen or so older adults, and they would see the latest iteration of the robot, and they would give us feedback. And they'd be like, yeah, I do not want this robot recognizing my face, for example. I thought face recognition was a great idea. They're like, no, don't want that. Lots of other like very small details about the way that the gestures were done, the way that the voice, the design of the voice, the kinds of things that the robot said, and so on, were designed in collaboration with the older adult. And in order to do this, it is like extremely hard because you're dealing with a community of people who are not only older and maybe not all that familiar with technology, but they're also living with dementia, so they don't necessarily remember session to session what happened. And you're trying to help sort of teach them about artificial intelligence and teach them robotics so they can give you meaningful feedback and so on. So the sort of impact of this project has been many, many, many papers and lots of students and all kinds of things. But I actually think the actual impact of this paper, this project has been far greater because we put this sort of humans first in the way that we did this. We didn't just design a bunch of technology as would be my tendency, and then just put it into the robot and be like, here, older adult, here's your robot, have fun. We instead involved step by step the older adults in the design process. And so, like, you know, there's these like wonderful quotes from people who talked about how wonderful the actual research project was for them, both like students in our lab who were very excited about it, but meaningfully like some of the older adults themselves. So we had some older adults who died during the project, and the family members said, for example, I'm so grateful for you giving him something so real to contribute to in his last home, and how meaningful this research project was to him. And because of that, this project, I think, has had way more impact than any of the other computer vision related projects that I've ever worked on. So we've demoed this robot all over at K-12 career fairs. We demoed it in the US and Japan. It lived with older adults in Japan and the US for several months. We presented this at the AI for Good Summit in Geneva both last year and the year before. We were invited to present the robot at the Senate, the US Capitol. We had various interviews with people. There's a whole Wired magazine article about it and so on. And actually just last week, I won't show you this video because I'm too embarrassed by it, but there was actually a whole like little commercial that aired during the like football games nationwide about this robot. And I think the reason it struck this nerve is because we had this human-centered kind of process for creating it. And so I started this talk with the title Human-Centered Computer Vision. I don't really know exactly what that means, but I just think that as we think about all of the changes that are happening in our community, how quickly it's growing, as well as like these like giant existential things that come in the news these days, like on one hand, like on the same day you see a headline about how AI is going to lead to world extinction and how it's also going to save humanity. And we're like, well, how do we as computer scientists like navigate this that's happening in our field? And so I would argue that two things. First of all, I think it's very important that we think about how to keep people at the center of what we're doing. And because I think that's really the goal that unites all of us, is we're trying to make the world a better place in the long term by making people's lives better. And then secondly, and most maybe more concretely, I'd like you to think about this idea of God tricks, of things that we treat as objective that are really subjective. What are the assumptions that we bring to the problems we're trying to solve? What are the assumptions that we bring when we evaluate our algorithms, when we compare to other people, when we collect data sets? Because there's a lot of them. And we can't stamp them all out. Maybe we shouldn't do them. But I think it makes sense to at least be honest with yourself and others about the kinds of people. And with that, I will just say thank you so much for listening to my talk.
Thank you so much, David. This is really inspiring and worth a lot of thoughts. Any questions from the floor?
After 6 hours of listening to us talk over the last 2 days.
Actually, I'm curious about the one you talk about, the aesthetic quality assessment, because you may know you may remember one of the tasks I'm working on is on the risk assessment, and I felt risk is also something similar. It's hard to determine, have a one single matrix to say, okay, this is risk. And recently, we actually checked the crossing reports, and then they have in the literature of that, you see like tons of metric developing like different metric for that. And then the question is, what should we use? There are a lot of these metrics, objective metrics, but now we have this new scenarios, and they wanted to quantify it. So we were thinking about, we have some selection of that and then maybe get a subset of metrics. Then the question was, how can we continue to do that? So I think the one, we were discussing having human involved, but still not really sure. Okay, now we have this matrix, for example, like 10 of them. Do some process, we get 10 of them. Then we wanted to see what would be the way we can somehow utilize these 10 matrices and also with the human involved. But that also become a question like how many people, who is going to, what kind of people wanted to pick? Are they the experts in the field, or they are non-experts in the field, or something like that? Do you have any insights from that particular work? How would you, if you were me in this position, how would you conduct this?
Not really, but I think I think it's important to clarify that, I mean, you didn't say this, but it's important for me to clarify that what I'm not saying is that quantitative metrics are bad, and what I'm not saying is that like common public benchmarks that we all use and data sets we all use are bad, because actually I think there's no way to argue other than those have really pushed the field forward over the last like 50 years. I mean, 15 or 20 years ago, everybody had their own data sets, and they had no way of like, you know, they would run algorithms on like a couple of images that they happened to download, and there was no way of even comparing things. And so those benchmarks have really created the opportunity to push the field forward in many different ways. But I just feel like that there's a point where you have to be honest. We have to be honest with ourselves that optimizing those numbers is not the goal. Like, the goal is not to write a paper with a results table that has slightly different numbers than everybody else's, because then it leads to like engineering specific data sets, engineering specific metrics, and so on. So I think like all of the assessments you might make of risk, they're like all probably potentially valid, but I think you just have to be honest with yourself and when you write the paper that like you're clearly not arguing that any one of these is the objective measure. There are different perspectives or different viewpoints on some very complicated multi-dimensional things that can't really be precisely captured on that.
Thank you so much. Any other questions from the audience? Yes.
Thank you very much for a very exciting talk. And then I also have a question about the table that their image processing researchers often shows. To be honest, I'm not there so I cannot say not so much convinced by that table because the conditions are different and also the setting are slightly different. And then I also think as a robotics researcher, I think that embodied their experiences is crucial to overcome the current limitation. And I also know that there many professors are working on robotics are actually coming from computer vision field. They started the computer vision, but then they also recognize that there is a limitation only using the vision. And then they started working on the robotics, which can integrate the multimodal signals. And I'm wondering whether, also you mentioned that the researchers in the computer vision are not always seeking their higher performances, but then what would be their like a current direction for the computer vision researchers, whether they still try to reach their much better performances in the visual processing, or if some of them are also recognize that they're more like a multimodal processing might be important, or if there are any other directions they may go in the future.
That's a great question. I think maybe like 10-ish or 15 years ago, I think there was this perception that computer vision papers should just be about imagery. So it was like, the argument was like, a person can see just a photograph and figure out what's in that photograph. So anything else would be, any other information you give or something would be cheating. That has really totally changed over the last like 10 years. So now, probably most computer vision researchers have done something with language and vision or audio and vision or 3D representations of the world and so on. So I think it's no longer controversial that multimodal is important. I think the embodied part, you're right that it's a small but sort of rapidly growing area, and I think, I'm not sure if like everyone in computer vision right now would necessarily. So I would say that like one of the obvious missing links in this whole thing is embodiment. I think that's obvious to me. I don't know if that's what the average computer vision researcher would say or not. And it's a little bit hard to tease apart because, of course, well, I think robotics is way harder than computer vision. At least it's harder to get into because I can't just download a robot from my lab and start playing with it. I guess I can play in simulation and so on. So I think some of it is that it would take time for people to move into that area, and so they're sort of comfortable in the benchmarks and problems that they're working on right now. But I think in the long term, I think there's no question that embodiment is in the same way.
Thank you. Yeah, interesting.
I would like to ask, how would you define the subjective or objective? Since in my opinion, like all the research and experiment is done by human. So we probably hold some bias or our opinion to do this research. So I think there must always be subjective work. So how would you define it?
Yeah, I conveniently did not define it. I don't think I really have a definition. I mean, I think probably, well, so I think you're right. I think basically anything that we think of objective is probably really at some level subjective. Because at some point in the process, there was a human involved in making decisions about what to measure, what not to measure, what result to report, what result to be like, oh, that was an outlier, maybe I'll just forget about that one, and so on. So, but, I think you can imagine sort of this spectrum of things where, like, some things in the world are probably countable, and whoever counts will probably get the right answer, get the same answer no matter how many people, like, count that number of things or something like that. So that might be very objective. There isn't a lot of disagreement. And then subjective things might be things where, like, there's a lot of disagreement. There's not a lot of agreement across different observers of the same thing. And then I think what I'm arguing here is that I think most of us in computer science think of the work that we do as extremely objective. Like, we prove property, we write code that's correct. It always does the same thing every single time. We're measuring properties of the world. We're trying to maximize objective functions. It's like this purely objective, quantitative sort of trajectory or goal towards something that is very well defined. We want to maximize everything. There's something we're trying to maximize. There's a model that will work the best, and we want to find that model. We're all taking steps towards that. And I think what I would argue instead is that a lot of vision is not that objective. There probably isn't a single model that would be the best model. There's probably not a single model that will get the best results on any result table that you create because vision is inherent. I guess that's my point. Thank you.
Other questions?
Yeah.
For your the data you show that nowadays the paper will show the tables to. I mean, I can imagine like how would you tell or convince people like your paper is, I mean, novelty or something has any contribution to the society without like the data or something? Sure.
Yeah. So, well, imagine like when computer vision came. Some of the very first papers in computer vision were during the 1970s and 1980s, and then you might have one image. Like you have a single image. Only a single image will fit in the memory in the computer. Actually, the whole image won't fit in the memory in your computer. You have to like, go through it in pieces or something like that. And so the papers back then, they would literally show the output of a single image, or like 2 or 3 images, and so this is the result of our work. Now we have like these gigantic data sets, and I think neither one of those is the ideal because it's hard to argue that what you do on a single image is somehow representative of the whole world. I think now we have these gigantic data sets with tens of millions of images, and so if you can sort of lazily say, well, that evaluation is way better than the single image evaluation, except that like probably most of us have never looked through the million outputs of our algorithm, or even maybe one output of our algorithm, so we don't really actually know what's going on in any of the images, whereas back then they knew every little detail about what was going on in that image. So I guess there's two answers to your question. One answer is that there's other kinds of vision papers that you could write. You could write papers that prove properties of things. You could prove the correctness of something and not necessarily need empirical results. But you're right. I think in this day and age, the kind of work that we do, you're almost always going to have a results table of some kind because you need some quantitative evaluation to real unwritten. That's what the
I think both both of you have talked about the illusion or the ambiguity of vision, and so I want to know that since humans have this kind of symptom that when we see something, that image may cause us feel that we see something that is not true. That's not in the image, but we think that it is. Like the dress, it's actually a blue dress and with black strip. But some of us will think that it is a white dress with golden strip, or like the two regions of the square, they actually are same color, but we don't think that one of them is a orange and one of them is brown. I want to know that, in your opinion, is that telling us that our vision system is not perfect, or what could be the perfect vision system?
So I think it's really important to remember that we think of vision. Most of us just naturally see the world without even thinking about it, and so we think that the sensation of vision is like measuring this objective truth about the world around us. And that's not really what's happening, right? There's like a 3D world around us. There's photons of light bouncing around. Some of them hit us in the eye and the back of our retina. We get a 2D projection of the 3D world. And from that, we have this illusion that we understand the 3D world around us. And like UJ said, we have very low resolution and the peripheral vision, and yet we have this illusion, like right now I can see him right there, and I think I see him in color and high resolution, but I don't. It's this illusion. And so like it's not even clear like what the right answer is here, because like white and gold and black and blue, those are just like human constructs. They're sensations that we see. They have nothing to do with the physical world. The physical world is bouncing light around with different wavelengths of energy. There's a whole spectrum of light that hits you in the eye. The blue that's coming off right now, that projector, is completely different from the blue that you would have if you actually had the dress here in person. They look the same because of all of this engineering work that understands the average human, so they trick you into thinking that stimulus is the same as the blue dress, but they're completely different. And if there was another animal here, they might see these colors in completely different ways, and the birds would see infrared, and so like the experience that we get it's just a sensation of the world, and so it's hard for me. You might have a better explanation, but it's sort of hard for me to even say what is right or what is wrong, because it's all like defined in terms of these sensations that we get. And we've defined vision in terms of the way that we egocentrically, selfishly see the world. We talk about visible light. The only reason it's called visible light is because we can see it. If humans weren't on Earth, it would just be any other little band of light. There's nothing special about visible light if we can see it. Yeah, so I don't know. That was a long ramble. Didn't answer your question.
Thank you.
Other questions? last question, a bit controversial. Well, I actually wanted to hear both of your thoughts on that. So there is a very famous neuroscientist and then vision scientist called David Marr. One of the best the best paper award of ICCV, International Conference on Computer Vision, is called Marr Prize to recognize his contribution. The question was actually kind of following that. So they had David Marr set down these 3 layers of theory. The first layer is what is vision is a computational machine. So they have computing theory, and in that book he defined vision is to reconstruct 3D. So he defined this task and then showed us what are the possible things we have to compute in between, like I think 2.5 the sketch, prime sketch or something, and then 2 3D representation. And following that, I think that task, I don't think is the answer. We know that because actually we do more than that. So we're not just computing the 3D, but more than that. So actually, today, I think we talk about, both of you talk about a lot of the human thing. So I was kind of questioning by myself, kind of believe that this hierarchy, you have this computation theory, you have the algorithm, you have hardware. So kind of really nicely to put many different fields into this particular framework. But on the top, we said, okay, vision is to compute something. And I believe in Yuki's work, I think we can somehow say vision, not necessarily vision, but I mean our multisensory perception is to predict the multisensory signals, and somehow they interact with each other. So I'm curious about from the question everybody is looking at differently, and then we have this human perception. I mean, human center means we always have others around us. So is it still, I mean, able to say we are still computing something or more than that? So I think my question is more about questioning about this framework. Is it just something hold when we were talking about social interaction and vision just computing something? That's it. Yeah. I don't know. This is a really, I don't know, question. Just due to the discussion of these 2 days, I started to question about this particular framework. Even though it sounds nice, but not sure is it possible to say, okay, vision is doing this task. And we don't know the task yet, but is it able to say vision is doing this task ultimately? Does it make sense, my question?
I'm not sure I'm smart enough to answer the question, but I mean, I think what I might be arguing here is that I think it makes sense to think of vision as computation. Like yesterday, you guys were talking about prediction and how the brain is trying to predict things in the future, and so that's sort of you can think of that as a computational task. And I guess what I'm sort of trying to argue is that there is not one single correct computational model to describe what we should be doing. Either computer vision is probably perfect because each of us is different embodied ways and things also. So I think there's this view in computer vision that we're all, we write objective functions, we're trying to maximize an objective function. It's kind of this implicit assumption that there is a correct model out there and we just have to find it. And I just think that that's fundamentally wrong because there's many different ways of experiencing the world, even if each of us individually is doing some computation. But I'm not sure. You probably have a much better answer.
Might be different answer from the robotics perspective. That we think that traditionally the people were saying that the perception comes first and then we create the action. Perception action line is a one process. For example, the robot would also take. But this is not like a feed forward process, but it should be the circle, like link. We perceive the world because we want to act on the world. And then our action change our perception. So this the perception, not only the vision, but all types of the perceptions are for acting on the environment. And then this action can lead to the next perception. So we always in this loop between the perception and action. Although we don't want to separate perception and action, but then from the robotics point of view, we say that the perception is closely linked with action, and action also influence our next perception. So we have to always think about this way.
Yeah, I think that's also possible to put it into this computation task. I think still possible. It's just how you connect the output to your input. I think that's still possible. I think it's just, I have this new thought that this input's actually coming from many different aspects, including your visual experience, your hearing experience, but also another mind. Means another computational machine is doing something. And now, if we only say whatever this mind, so output will be the input of ourselves. Is it a way to frame it? I think this is what where my question coming from. It's still possible to frame it this way, or do we need to think it differently? Yeah, that's the general question why I'm asking this. Anyway, I know this is open questions. There are no clear answer to it. But anyway, thank you so much. And again, thank you all your attendance, and also definitely really appreciate David and Yuki's really insightful and then thoughtful presentation. Really learned a lot from the past 2 days. Really appreciate it. Let's give them a warm welcome. Thank you so much for them. Thank you.
Thank you so much.